So yes, the lecture will focus on polynomial automorphism, and maybe mostly from the group theoretical point of view, not so much dynamics, but it's kind of you have to understand the group of polynomial maps to do the dynamics after. So it's the first step. In the first 20 minutes or so, I want to present you these objects, the polynomial automorphism, and also what kind of question I want to talk about for the mini course. So we're going to start slowly. Okay, so group of polynomial automorphism. So for the moment, I don't want to make any assumption on the dimension or on the base field. So say the dimension is n. And k my base field. So later, maybe k will be a characteristic 0, and maybe n will be mostly I will focus on 3, n equals 3, and n equals 2 as a toy model. But for the moment, any dimension, any field. So what is the group of polynomial automorphism? That's the following group. So aut kn. So it's some map from kn to kn, like given by in coordinate. If you have x, which is x1, xn, you map to f1 of x, fn of x. Okay, so you want each component, each fi is a polynomial. So that will be a polynomial map, and I want an inverse map of the same form. So f-1 exists and is of the same form. Maybe it's too small, maybe, or is it okay? Okay. Well, yeah, but in the far away, it seems okay. So okay, so it's of the same form. Okay, so that's a formal definition. Let me give you some example and maybe some non-example. It's nice to see what is not polynomial automorphism, just to have the right idea. So let's start with it. So for instance, this one, take f of x1, x2. So in dimension 2, take this one, x1, x1, x2. So for sure, it's a polynomial map. It is invertible in some sense. It is birational. But the problem is that the inverse is rational but not polynomial. So f-1 exists. f-1 is x1, x2 over x1. So it will fit in the group of a birational map of Kn, but no, it's not in my group because it's rational, not polynomial. So this one, it will be in the group B, Kn, but F is not in aut, sorry, it's 2, K2. Another one, which is not good. So let's take K to be the field of real number, and just in dimension 1, sufficient to give the example. So you go from R to R and to X. So, you take X to the cube. Okay, so it's polynomial. It's bijective. Okay, but it's not in my group because inverse is not a polynomial. So it's so of course you can do example with more variable, but already with one variable. You should keep in mind that bijective is not the same as automorphism.
But if the field is not closed?
Yeah, of course, of course. That's the next remark. Yeah. Okay, so I want to use these two easy counterexamples just to say that, as you want to say, secretly here I'm doing some algebraic geometry. And the real definition is not this one, it's a definition in algebraic geometry. So the good definition should be the following one. Good definition. You should say that it's really a polynomial automorphism. It does not really act on the point, it should act on the functions. So you should see it as a automorphism of the ring of a polynomial map. So that's what it should be. So it's if you want a good or equivalent definition. You look at the automorphism of the algebra of polynomial. Maybe preserving the constant. So if you have f1, fn defining a polynomial automorphism, you should think that it's also define automorphism of this algebra by substitution. You replace x1 by f1, replace x2 by f2. So here f, which is f1, fn. So the same one, I can see it here as an automorphism of this algebra by thinking of it as substitution. Or if you want, the f1, fn is another basis of the algebra K of x1, xn. Okay, so this group of automorphism of this algebra is isomorphic to this group of polynomial map from Kn to Kn. You should be careful that it is not exactly isomorphic, it is anti-isomorphic, meaning that it reverses the composition law. So if you, okay, I'm more on the dynamical side, so I like to compose in the normal way at the level of points. So when I write f on g here, I mean I apply a g on the point and then f. But when you do a substitution, if you compose the same one here, you're going to get g on f. It reverse. If you substitute, it's not the same as acting on points. So when you look at the literature on polynomial maps, there is an algebraic side of the story, and the people they think like that, so they compose in the other way. Okay, but it's a good way to see that. Yeah. So this one, if you substitute x2 by x2 over x1, you get an automorphism of the field of a rational function in x1, xn. So you should put some parentheses, and then you will get the birational group. And here you see that if you substitute x by x cubed, it's not automorphism of this algebra. Okay. Okay. And just just one more remark in this along this line is I'm okay to work over any field. So for instance, I'm okay to work over a finite field. And over a finite field, it's really not a good idea to think that the polynomial map, the polynomial automorphism is not the same as its action on the points, because you have only finitely many points over a finite field. So really, again, it's not the same definition. So let's give an example for that. So if K is finite, f in odd Kn is not characterized by its action on Kn, which is finite. So for instance, just to have a concrete example, if you do in dimension 2, x1 plus x2, x2 minus 1, x2, for instance, over the finite field with 2 elements. See, so it's exactly the same. If you put 0, if you put 1, you have nothing here. So it's exactly the same action as the identity, but it's not the identity automorphism. So this one has the same action on f2 square. So on f2 square, you have only 4 points. I mean, so the same as the identity, but definitely this f is not the identity. So again, either you think of it as a substitution and you say, okay, at the level of algebra, I'm doing something, I change x1 by another polynomial. Or if you, like me, if you prefer to act on points, the real way to think of such a map, it's a map that acts on the algebraic closure. So it acts on f2 bar square. So now it's not the identity because you have many, many points where it's not the same. Just it's given by the coefficient are in f2. So should think that f in odd Kn acts on, in fact, that's what I mean by we do secretly, we do some algebraic geometry, we act on the algebraic closure, and this is just to remind ourselves that the formula are given over K, but the action is here. And then you solve this kind of problem. Okay, so so maybe the trivial case is n equal 1, but you have nothing interesting because it's only the affine group. So polynomial map, I mean, odd K in as a K1, if you want, it's just an affine group. So it's all the map of the x goes to aix-marseille. Okay, so the first interesting case is n equal 2, and n equal 2 already it's a quite interesting group where you see some map of automorphism where the degree is not 1. So I give you some first example in n equal 2. So it's interesting group already. So it contains a map of this form. If you have x1, x2, you can send it to x1 plus an arbitrary polynomial in x2, comma x2. And if you compose this one by the exchange of the two coordinates, you get some map of the form x2. So maybe I just take the polynomial x2 to the d plus x1. So these maps are the Henon automorphism that came up before the day before. So that's Henon maps. I guess we call that Henon maps over C over R. Okay, so you have interesting maps to do dynamics if you want. And starting from dimension 3, it's an interesting group also, but it's probably too big, too large, too fully. So it's too complicated to be fully understood for the moment. So complexity comes quite fast. Case n equals 3, it's a huge group. Not well understood. So even at the end of the mini course, it will still be not well understood. So it motivates the fact that we, as the title of the mini course suggests, I will not focus really on the full group of polynomial automorphism, but on the subgroup, the Tame one. The Tame one is so that I can answer some of the question. Okay, so we will focus on the subgroup, the so-called Tame automorphism group. So it's quite a naive definition. It's just this kind of automorphism. You have them in any dimension. Just you do something on the first coordinate. After that, you do nothing on x2, x3, xz. So at least you have that in any dimension. Also, the affine group is always there. So affine group in dimension n. So at least you have the linear group, and translation are just you do that with p constant. So you always have the linear one. You always have this kind of translation with parameters, and it's natural to look at the subgroup generated by this, and that's the definition of the Tame automorphism group. Okay, so this one was. Okay, so by definition, my group denote Tame Kn. That's by definition the group generated by the linear group over K and this kind of elementary automorphism of the form x1 plus a polynomial in x2 xn, comma x2 xn. So these are elementary. And this is a linear one. Okay, so it's as a subgroup of the full group. So sometimes we define that as generated by affine and triangular. So triangular means you do the same, but maybe you're going to put some coefficient and you're going to put some x2 plus a polynomial in x3, xn, and then each time you have one variable less. It's the same. So if you put affine, you don't need the translation because the translation are already there. P could be a constant. So if you have x1 plus 1, by conjugacy under the linear group, you have all the translation. So really, I have the affine group here. And also in GLN, I have the permutation. So if I conjugate this one by a transposition of x1, x2, I can put this polynomial here, and then I get everything. So it's a kind of the smallest generating set for that. Okay. So let me give you some facts on this group, because the natural question is it really a strict inclusion or is it equal? So I just state the fact. After that, I will ask some question on this group. After that, we will really start the mini course answering the question. Yes, Charles?
Why is it called Tame?
Because it's not wild.
So the group is Tame or is element in the...
No, what I mean, Tame here is probably just we understandable. Yeah. That's, and I think there is no deep meaning. Yeah. Who calls that Tame? I'm not even sure. Yeah.
Do you maybe have an example of why it
Yeah, but yeah, okay. You're right. At least it's you should ask the question after this statement. So let's put some facts. Okay, so n equal 1, it's trivial. So n equal 2, in fact, it's an equality. So that's the first result. That's why it's interesting that we can study in dimension 2, because in fact, every automorphism of K2 is tame. That's a starting point of understanding everything. So for n equal 2, you have an equality. So tame K2 is odd K2. And in fact, so that's known as Young theorem. It was proved in the 40s. And there is a second part of this result that we will see later today. Okay, so for the moment, here it's any automorphism here it's generated by that, and after that you can ask what about the relation. So that's the second part that will come later. Okay. And for n equals 3, then you have to put an assumption on the field, characteristic 0. We know that it's a strict inclusion. So Tame K3 is strictly contained in odd K3. Okay, so that's due to Chestakov-Umyabov. It's around 2001 or 2, I don't know. Where they essentially they give a algorithm given a automorphism to decide if it is tame by the algorithm is if it is tame, you can reduce the degree by some elementary operation. So if you can go down to the identity, it was tame, and if at some point the algorithm is stuck, it's not tame. And also we have in fact explicit example where the algorithm cannot start, so it's really here and not here. And okay, I'm not going to write the example, but it's not very complicated. It's degree 5, so mildly. And it was it was proposed by Nagata in the 70s, like 30 years before. So we had the counterexample for a very long time. It's just we had no way to decide if it was here or not. Yes, another question.
Do you have an example of a normal subgroup that contains tame K3? Non-trivial one.
Normal. Yes, that's. I guess not. Yeah, maybe. For instance, the counter example I have in mind, Nagata, is conjugate to. So probably. So my feeling is that if you take the normal one, you're not going to get everything, but we have no access to that. And if you remove the assumption, so characteristic P, it's open because the algorithm they have, it relies, the estimate on the degree, it relies on some estimate of the derivative. So when you take derivative in characteristic P, you have some problem. So that's why the statement is in characteristic 0 only, and for higher dimension, we have no idea. So probably it's still strict, but it's an open question. So it's open for other cases. Four dimension. So in dimension 4, for instance, it's not known if tame K4 is strict or not in odd K4. Okay. And for instance, you could say, okay, I have my concrete counterexample. It has it is in dimension 3. Let's extend it to a 4-dimensional example, but just putting x4 goes to x4. Then it is in tame K4. This we know. This we know. So, but we have another candidate to be not here, and we don't know. It's called stably tame. Stably tame. When you adding some variable, you become tame. Yeah. Okay, so I'm not going to. my focus for the lecture, I'm going to say the Tame group is interesting in itself, and I'm going to study group theoretical question inside this group. And so I just wanted to state this fact for the picture, but I'm going to concentrate on the small group. So in dimension 2, it's the same. In dimension 3 or more, a priori, it's a subgroup. So question, yeah?
Is that Tame and amalgamated products of the
So for Tame K2, that's the second part that's going to come. You have you know the relation, it's a free product with amalgamation. For case 3, you will see I will go around this question exactly. Yeah?
The algorithm to check if something belongs to Tame 3 works in our dimensions? Or
I don't know. If it was working, the question would not be open.
You don't know if there is something.
We have the candidate. We have the candidate not to be not Tame, but we don't have the algorithm. Okay, so what kind of questions I want to ask about this Tame group? Okay. Before asking the question, I should make easy remarks. So about normal subgroups, there is an obvious normal subgroup here because there is an obvious homomorphism, which is taking the Jacobian determinant. So remark, there exists homomorphism. So even from hot to K star. So starting from F with a coordinate F1, Fn, the component F1, Fn, you take the Jacobian matrix, and you take the determinant of that. So a priori, it's so each Fi is a polynomial. So here you have a bunch of, it's a matrix with polynomial entries. But you know that it is the map is automorphism. So it is globally invertible. So for sure, it is also locally invertible. So it means that locally the determinant is not 0. So you have a polynomial. The determinant is a polynomial which is not 0 at each point. So it should be a constant. And of course, the big conjecture is that if you have a polynomial map and this determinant happens to be constant, so you are locally invertible. Is it true that you are globally invertible? Is it true that your map is? So that's the Jacobian conjecture that I will not discuss at all. Is that you should not, especially young people, you should not try to solve this problem. I think I'm not old enough to try to make a false proof of that. So, okay. So since you have this homomorphism, you have the kernel. The kernel maps automorphism with determinant 1. So let's call that the Jacobian of F. The determinant is. So if the Jacobian of F is 1, you are in the subgroup. It's similar to the special linear group. Here you have the special automorphism group. So that's obvious normal subgroup. So then the not obvious question is there some other, so smaller normal subgroup inside this one? Okay, so let's start with the question. So let's do that. Yeah. Yeah, but again, that's why I made this remark at the beginning. In fact, I'm working on the algebraic closure because my automorphism of Kn, in fact, it's on K bar. It's just the coefficients are in K. But when you ask this kind of question, you should really think that you are. So I know that there is a version of the real Jacobian conjecture, where you instead of saying constant, you say always strictly positive. But I find that it's not a good question. You should really say, you should ask the question on C, extend to C, then it's constant, that's a real question. Okay. Just personal opinion, I guess, yeah. Okay. So questions? So, okay, so it's about Tame Kn. So, of course, each question you can ask about hot Kn. Just for Tame, sometimes I can give an answer, and for hot, never. So, okay, you can ask the question, but so that's why I restrict to the Tame group, so that it's reasonable. So first, the first one is question about normal subgroup here. So apart from the kernel of, okay, I didn't give the definition. Let's do that. So my notation for the kernel is S hot, S like special S hot, Kn is the kernel, so it's the F in hot Kn with Jacobian 1. And similarly, you have S Tame with the same condition. So the special automorphism, special Tame automorphism. Okay, so the first one is what about the normal subgroup? In this S Tame of Kn. So about existence. So do you have some interesting quotient of this group? Another one is what about the finite subgroups? So you, can you classify up to conjugacy the finite subgroups inside Tame? So what do I mean by classify? If you have a group of a linear group, you have a finite group of symmetry in GLN K. So it will be here. And then if you have a finite group in GLN K, you can conjugate by any Tame automorphism. So essentially the same finite group up to conjugacy. And the question will be, is it true that any finite subgroup is of this form? It's a conjugate of some finite group which has inside the linear group. It will be the linearization problem for finite subgroups. And you can ask the same kind of question, replacing finite by algebraic. So for instance, you could ask, is it true that any additive one parameter group, additive or multiplicative, is conjugate to a linear one? So you can replace finite by algebraic. For instance, one parameter subgroup. By one parameter subgroup, I mean either K plus or K star multiplicative. Okay. And another one, a group theoretical question. You can ask about, so here it was about normal subgroups, about finite subgroups or algebraic subgroups. You can also ask questions about all subgroups, and then one way to put it is to ask for a Tits alternative for this group. Tits alternative for Tame Kn. So Tits alternative is the following question. You take a subgroup of your group. So is it true that for any subgroup G in Tame, well, you have the following alternative. Either G is quite simple group in the sense, so not in the sense, not in the sense that it's simple for group theory. It's solvable, so almost abelian in some sense. It may be so solvable up maybe to finite index. So for all G, either G is so up to finite index, we say virtually. So solvable. You take commutators and commutator of commutators. You have the sequence of subgroups. At some point, it becomes identity. So it is not too far to being abelian in some sense. So that's one side of the alternative. And if it's not the case, then you're going to have a strong obstruction to be solvable. Is that the group contains a free group over two generators. G contain, so this is a free group F2 over two generators. So free product of Z with D. So that's a Tits alternative, which is, it's called the Tits alternative because Tits proved that it was true for any linear group. So it's a question, so this fact is true for a linear group. Is it true also for polynomial maps? It's quite a natural question. Just to put a question which is, so this question in my mind are in fact related to dynamical question as a first step. For instance, it was mentioned by Gabriel Vigny that long time ago I proved that if two Henon maps have the same current or the same green function or Julia set variant, then they have a common iterate. And in fact, the proof is because I understand over K2, if they have say the same green function, I know something on the commutator. The commutator should respect the green function of one is the other. So the commutator should be non-Henon, and so it should not be on this side of the story. So it should be solvable, and I understand completely the solvable subgroup, and so I have the answer. So even if it's the question is asked in a really in a group theoretical terms, after that, in my mind, it's a first step to answer maybe some dynamical question about symmetries of the action. And for the last question, really, I want to put dynamic in the question. So I can ask, what are the possible dynamical degree of such maps? That's also an interesting question. So in a Tame. Okay. So here so let me write again the definition of dynamical degree. So for when you have f, which is f1, fn, so each fi is a polynomial, so each fi has an ordinary degree, and the degree of f is the maximal of all these degrees. So by definition, the ordinary degree of f is the max of the ordinary degree of the fi. Okay, so that's an ordinary degree, and then you use this ordinary degree to define the lambda f, taking the iterate of f and 1 over n and limit of it. Okay, so the degree are submultiplicative. It's easy in this case, and so the limit exists. And I call that the dynamical degree. It's the first dynamical degree, but I will never consider the other one. So it's lambda 1 if you want. Okay. So for instance, there is an idea that maybe the dynamical degree should be in this restricted setting. There should be algebraic integers, and maybe even algebraic integers of some given of the algebraic degree. So if over Kn, it should be an algebraic integer of degree at most n-1. That's the conjecture. So we have some ideas that the dynamical degree should be particular numbers. Okay. Okay, so that's the questions. So now I'm going to try to answer some of them. That's the purpose of the mini course. When n equals 3, and I'm going to need some assumption, k is going to be characteristic 0. Okay? And in fact, for k is 3 characteristic 0, at the end we will have an answer for most of the question except the last one. And I will take as a toy model the case of dimension 2, where here I have answer for everything. And it's really a toy model because the way to make the proof are similar. And in dimension 2 is simpler. So, okay, so the tool to try to give answers. So you see that the group is given as a group of transformation of on Kn or K bar n, the algebraic closure. So it is defined as a group of transformation, but I'm going to try to make it act on another space, which is better to answer this kind of question. And the new action is going to be on a metric space. And I would like a metric space with some non-positive curvature, which I don't have for the initial action. So construct some action of my group on some metric spaces. With some non-positive curvature property. So with some form of non-positive curvature. So here the keyword for technical word for non-positive curvature, there will be two flavors. So one is called delta hyperbolicity or Gromov hyperbolicity, the same. And another one is cat zero condition. Okay, so that's why I have a S to the action because I will have several actions depending. Sometimes it will be this kind of non-positive curvature, this one, sometimes this one. And if we are lucky, that's the same space with both properties, but for case 3, I will have one space with this property, another space with this. Okay. So, so today I want to discuss the first construction, which in dimension 3 will turn out to be delta hyperbolic, and I will be able to answer the first question. Okay, so that's my goal for today. And maybe this afternoon. And tomorrow, we will see more a space with a cat zero property, and it will help to answer the finite subgroups and the Tits alternative. Okay, so I'm going to give you a construction of a metric space. So the construction I can do for any field and any dimension. Okay, so my starting point is going to be very general. But after that, I want to ask, is it true that it is a delta hyperbolic, or is it true even that it is an unbounded metric space? And when I want to answer such a question, I have to restrict to dimension 3 and characteristic 0. Okay, so the starting point is very general. In fact, we don't need at all to use the bottom, except if you want to use the top one. It's a simplification for. Okay. So first construction. So I'm going to describe an action of my Tame group, Tame Kn, on a simplicial complex. So it will be C, simplicial complex. Of dimension n-1. Okay, so for my two main cases, n equal 2, it will be an action on a graph, in fact. And for n equal 3, it will be an action on a triangular complex. But first, I give the construction for any case. So n any integers and k any field for the moment. So I want to define a simplicial complex. So I have to give you the vertices of this complex, and I have to explain how I glue some simplexes on my vertices. So first, what are the vertices? So I take, so it's an abstract definition. So vertices are equivalence classes of maps. So I think, so I take a map, so I guess I'm going to, yeah. All my maps are F, whatever. So F is a map from Kn, the dimension, to Kr. So this R is between 1 and n, and I'm defining a vertex of type R. So defines a vertex of type R. So R is between 1 and n. So for instance, for n equal 2, you have vertex of type 1 and 2. N equals 3, you have vertex of type 1, 2, and 3. So what do I ask for this map? So to x, x is x1, xn. I have f1, fr of x. So everything is polynomial, and I want this f1, fr to be extendable. So there is an extension, fr plus 1, fn, so that it becomes a Tame automorphism. So it's like the first R component of some Tame automorphism. So if we can extend F as a Tame automorphism, so F1, Fr, and then you extend, so you add some polynomial, Fn, and it really becomes a map from Kn to Kn, and it's invertible, and it's Tame. And then I claim that my first R component were a vertex of type R. So not exactly, it's a vertex of type R. It's such a map, but up to equivalence relation. So the equivalence relation is up to post-composition by an affine map in dimension R. So if they differ by post-composition by an affine map, I consider that this is the same vertex. So it's up to post-composition by an affine map. So from in dimension R, Kr to Kr. Okay, so if you have if A is in GL and K, so linear and translation. So this is my affine group. If you have A is an affine, so it's this is an affine group of Kr. I consider that F and F composed with A are the same. And I put some bracket to denote the equivalence class. Okay, so really that this is what I identify to a vertex. It's the data of such a map up to such equivalence. So this is a vertex. So soon, I guess for the first picture, I will put the bracket. After that, I will forget about the bracket, but it's always equivalence classes. Okay, so this is a set of vertices, and now I want to explain what are the simplexes. So yes?
So the element A is an affine transformation on R.
Yeah, exactly. So it's R, it's here, yeah? So A is here.
Also in GL and K.
Yes, it should be GLR. Yeah, you're right. Thank you. Thanks.
And just to be sure that your semi-direct product is also reversed.
Okay, I agree with that. I have to concentrate very hard for each one, though. Thank you. Okay. So simplexes. So I'm going to associate a full dimensional simplex to each element of the Tame group. If I have so now I start for each. So I did not everything F, but or maybe let's put G. G is G1, Gn. So now it's a Tame automorphism of Kn. So you see, I can associate a collection of vertices to this map. I can take just the first coordinate, it's a vertex of type 1. I can take the first two, it's a vertex of type 2, and so on and so on. So I have my collection of n vertices, and I glue a simplex on these n vertices. Yep. So we glue n minus 1 dimensional simplex on so the class of G1, the class of G1, G2, so the class of G1, Gn. Okay, so this one G1 is the same as A G1 plus B because it's an affine group of dimension 1 acting. This one is the same as A1 G1 plus B1 A2 G2, say A2 G2 plus A3 B1 G1 B2 G2 plus B3. So, okay, it's always up to a affine map. So you see here you act only with a one-dimensional, here with a two-dimensional, and so on. Okay, so that's a formal definition. We have a simplex. So of course, the first time you see that, you see the definition that you don't understand. So let's do some example and let's try to understand what does it mean in dimension 2, where we have a graph here. And it's already interesting. So in dimension 1, it's not interesting. You have only one vertex, so it's not a big complex. Dimension 2 is the first interesting one. Maybe I should say, yeah, I should put the action here. So it's interesting because I have an action and it's a metric space. So I should make this remark first. So we have an action. The action is by pre-composition by Kn. So you have, if you have G in Tame acting on a vertex of some type, so F1, Fr, by definition, you just want to pre-compose, and if you want a left action, you pre-compose by the inverse. So it's F1, G inverse, Fr, G inverse. Okay, so that's a natural thing to do. And so it's an action that preserves the combinatorial structure. And you can think of your simplicial complex as a metric space. Just you put the standard metric on each simplex, and you have a metric on each simplex. After that, you do the classical thing that if you have 2 points in your complex, you take any path going from one to the other. You can estimate the length of the path in each simplex, and you do an infimum over all possible paths or all possible chains. Okay. So, yeah.
So when you listed those vertices for this, that just includes in that order G1 and then G2, 1, 2, and then 1, 2, 3. Not all combinations of are.
Yeah. For instance, G2, G3 is not here for the moment. Yeah.
Okay.
That's
so it's just that.
just in this order. Okay. The G2, G3 is somewhere else in the complex, because if you switch the coordinate, it's another one, but you will see it on the picture, I guess. Yeah.
Also, maybe,
Yeah.
so you're saying you have only n-1 dimensional faces, but I guess you have other dimensional faces in your complex?
Yeah, when I put the simplex, I put the edges, 2-dimensional, just in one scoop. Yeah. So let's start with case n equal 2. So here we have vertices of type 1 and 2 and some edges. So it's we really get a graph. So for instance, you have, so start with G, takes the identity. And okay, for dimension 2, I'm so used, I don't use x1, x2, I use x and y. Just easier, so let's do it with x and y. So the identity is the vertex of type 2, given just by that. And if you follow my convention, you have also a vertex of type 1, given by the first coordinate. So it's really, when you take G, the identity, you have this vertex of type 2, and this vertex of type 1, and 2 minus 1 simplex, so just a segment on this. So this is the construction here. So this was for G with the identity. But then to answer your question, Laura, you can also start with another one. You can start with this permutation, which is also an automorphism. And this one, the first one is y. So it's not this one. Y and x are not equal up to the affine group. So you have another vertex of type 1, which is the class of y. But it is also, so this one is the same as this one, because going from here to here, it's an affine map. So the 2-dimensional one is the same, but the 1-dimensional one is not the same. So you get this simplex starting from here, and you see there is a common point, and you see that you get something connected at the end. So in fact, you can play here. Here it's also ax plus by, cx plus dy. You even have the translation if you want. But the translation, here you have x plus c the same. So I don't put the translation because they are going to be killed even at this level. But here, for instance, ax plus by, it's another one. Okay, but it's up to the 1-dimensional affine. So if a and b are not 0, I can decide to multiply by lambda, and I can decide that one of them is 0. So in fact, is 1, sorry. So I can decide that this is x plus cy, just dividing by a. So you see that in fact, all the vertices which are at distance 1 from this one are parameterized by P1. You have a constant, you have AB in P1, because it's up to a scalar. So you have as many edges as a projective line over your field. So if you over C, you have already a lot of edges. Okay, and just to give another one, if you start with this one, x plus p of y, which was my elementary one. So you see that x plus p of y, it's it contains y as a coordinate, so it's going to be related to this one. So here you have x plus p of y. So this is another vector of type 2. So it shares, with identity, it shares a coordinate, so it shares a vertex at distance 1. But these two are not in the same class, because this is not of this form. Okay. So you should get an idea of the geometry of this graph. And now I give you a few facts about this graph. The first fact is that the graph is a tree, in fact. So it's equivalent to the following fact. So it's related to the following property. That okay, sorry? For n equals 3, it's not a graph. It will be a two-dimensional complex, and so the dimension is going to be. But it should be an illustration, this fact that it has some hyperbolicity property. Because if you have a loop in a graph, you see some positive curvature, and I claim no. It's a tree. It's as hyperbolic as it can be. Okay, so it's related to property that if you have f that you, so by definition, a Tame automorphism of K2, and in fact any automorphism, since Tame and auth are the same in dimension 2, you can write it as a composition of affine map and a triangular one. So you have A1, B1, A2, B2, AN, BN. So okay, so maybe it's not of even length, but I forgot to make a remark. So you see that the stabilizer of this vertex for the action is exactly the affine group. So here, the stabilizer of my V2, this one of xy. This is A2. This is a two-dimensional affine group. And the stabilizer of this one, of y, what does it mean? It means that it has to be an automorphism such that y is sent to maybe cy plus c prime. So in some sense, you preserve y, and it's exactly the triangular group. So this one is the group of automorphism of the form, so it's B2 in my notation, and B2 is defined as all map of the form ax plus a polynomial in y, by plus c. So that's called the triangular group. And the Tame group is generated by the affine and triangular, okay, because triangular contains my elementary and the affine contains my linear group. So these A2 and B2, the stabilizer of these two vertices, already they generate the group. And so I can use them to write any f. So the AI are in my affine group, but I can assume they are not triangular, and the BI are triangular, but I can assume they have degree at least 2. Otherwise, there is some simplification. And maybe I should put yeah, so except the first one and the last one, if you want to be called, because I'm not sure that. Yeah, okay. So, but what I want to state is a property about such automorphism. So if you have any product like that, the ordinary degree of f is just the product of the degree of the bi. So for any f, the degree of f is a product of the degree of the bi. Okay, the ai are affine, so degree 1. So just the bi have some degree, and the degree at least 2 by my assumption. So the fact that when you compose such a map, the degree grows, so it cannot be the identity. It means exactly that when you move in your graph, so when you go from one vertex to a distance 2, what you do is you're doing multiplication by elementary map and affine map. So you can interpret a path as a composition like that. And to say that there will be a loop will mean that the composition, at the end, you come back to something of degree 1. And because of this fact, it's not the case, so you have no loop. So you can translate this algebraic fact, that the fact that the degree grows and such a composition is not the identity, into the geometric fact on the graph that it has no loop. It's really a trick.
Do you prove it algebraically, or can you somehow prove it geometrically?
No. That, you know that, and hence you deduce. Yeah. Okay. At least for 2 days, that's the way I do it. Yeah. And also, my edge, my favorite edge here that defines the two stabilizers, you can see that it's a fundamental domain for the action of the Tame K2 on the tree. So the edge, so that first fact. The second fact is that the edge y, xy is a fundamental domain for the action of hot K2. Or Tame, the same. Okay, so then you have the general fact. If you have an action of a group on a simple tree, the fundamental domain is just one edge, then your group is in fact the free product of the two stabilizers, of the two vertices, amalgamated along the stabilizer of the edge. So you get some description of the relation on your group. So this implies that in fact your Tame group, which is also the full group in this case, so not only it is generated by my affine group and triangular one, but in fact it's a free product amalgamated along the intersection. And it's the fact that it's free product amalgamated to the intersection, it's essentially this fact that when you compose, you don't get the identity. So if you want this implication is in fact it's if only if you are an amalgamated product, if only if you act on a tree with a fundamental domain and edge. That's the easiest case of what is called the Basser theory. So we can say that this tree is a Basser tree of the group. So Young theorem is, for me, Young theorem is this equality that I do not discuss. And the Van der Kolk part is the fact that it is amalgamated, and this is just that. It's really easy. It's just, as the fact that the degree is that, it's super easy. Yeah. Just induction. It's 5 lines. Yeah. So this part is super easy. This part is not. This is 5 pages. So it's accessible, but it's not easy. So here you really need to do some algebraic geometry. You need to understand the combinatorics of the blow-up when you solve. So there is something to do. But here it's really a remark, the amalgamated product. Yeah.
For the fundamental domain, that line segment, are you excluding one of the endpoints? Or?
Yeah, because so the action sends a vertex of type 2 onto a vertex of type 2. So it's a graph with 2 colors of vertices, and by definition it respects the colors. So you cannot never send the black one on the white one. No? So really you need these two vertices included. It's not because you have in mind probably the fundamental domain when it's more continuous, and maybe one of the frontier is not going to be here because you have the translation. It's not like that. In fact, when you translate by at least two, no? Because it's two colors. If you want to translate, you have to go there. You cannot send this V2 to the V1.
So could you have an element that swaps around Y, moves it over to X, V1?
So this goes to there, but this is fixed?
No, V2 is fixed.
V2 is fixed, but this goes to...
Y flips around to X.
Yeah, so this is this one. This one acts like that. Change of coordinate. In fact, the stabilizer of V2, it acts transitively on the... In fact, it acts 3 times transitively because you know that for the projective line. Essentially, it's the projective lines. The action is it's an affine group. I don't know, maybe not 3 times. Okay, a good number of times. Okay. Mm-hmm. Yeah. This one? What? Yeah, it should be. It should be a remark also because any simplex. Any simplex is clearly the image of this one by the G I used. What you have to think, maybe it was not explicit, that the graph is connected. Okay, the fact that it is connected is because to go from 1 to a distance 2, it's always applying an elementary one. So since my elementary one are in my group, it's connected. Okay, so the connected part was maybe not explicit. Once you know that, it's clear that it's the fundamental domain is one edge. Yeah. I think so. Okay. No, okay. So let me give you some corollaries of this fact that we have an action on a tree. So consequences. So maybe the easiest one is about finite subgroup. So first, any finite subgroup inside my Tame group in dimension 2 is linearizable. It's conjugate to a finite group in GL2. Okay, so what I should say first, I should say a subgroup inside A2 or B2. That's really so when you have a finite group acting on a tree, there is a fixed point. That's where I use really the non-positive curvature. So you have a finite group, you look at any orbit, so it's a finite orbit, and when you have a finite set, or more generally a bounded set in a tree, there is a center, a circumcenter. That's the center of the smallest ball containing your bounded set. And because it's a tree, this ball is unique, so the center is unique. So this center should be preserved by your finite group, because finite group preserves the orbit, so it preserves the center. So that's really the way to use non-positive curvature, so here in an elementary case, but to have some fixed point property. So any finite subgroup is inside a stabilizer. The stabilizer are 2 types, either vertex of type 2, that's a affine group, or vertex of type 1, that's a triangular group. And then you can try to prove that if you have a finite group here or here, in fact, you can linearize, so you can go to GL. And for that, I guess you need some assumption on the field. So this is always true. And in fact, so maybe you need characteristic 0, I guess. Conjugate inside GL2, in fact. But my point is that the fact that you have a tree, you have a fixed point. So if you understand the stabilizers, you understand your final group, and you can, with maybe a little more work, you can do the same for algebraic subgroup. So my one parameter group, additive or multiplicative, I speak about at the beginning, you can also say they are always conjugate to inside that or inside that. Okay, that's the first consequence. Maybe the second one, I'm going to give you the answer for the dynamical degrees. So what are the possible dynamical degrees of polynomial automorphism in dimension 2? So it comes from following classification. So any f in my automorphism group is conjugate to one of the following forms. So it's conjugate to either an element in one of the stabilizers, in A2 or B2. And then in both cases, you see that the degree is always the same when you iterate, so the dynamical degree is 1. Or to a composition of this form, so with starting with A and ending with B, so with an even number of letters. So A1, B1, A2, etc., AN, BN. And so when you iterate, you have such decomposition longer and longer, and using the fact here that the degree is just the degree of the triangular one, you see that in fact the dynamical degree is just the ordinary degree of your map, so it's really an integer. Lambda f is so it's to such a composition, and the lambda f is a degree of G, which is also the lambda of G. Okay, so the dynamic degree is a conjugate invariant, so G is conjugate to f, so it's the same lambda, but for G is better because the lambda of G is also the ordinary degree of G. Okay, so really it's, in particular, it's integers. And it is at least 2, sorry, because it's a product of the degree of the BI. So it's a product of the degree of the BI. Mm-hmm. Okay, and so from a dynamical point of view, you use when you want to compute a dynamical degree, geometrically, you look for a good model. So you would like to find another model where your map is algebraically stable. So you want the indeterminacy point of f and the indeterminacy point of f inverse to be disjoint. So for surfaces, it works very well. For a birational map, you blow up, and at some points, the indeterminacy locus of f and f inverse are disjoint. Good, you're algebraically stable, and you do some your dynamical degree is the spectral radius of the action. But here, in some sense, it's simpler. You don't need to blow up to get the good model. You just have to conjugate. So the good model, so you have a map from, say, C2 to C2, if you over C. You compactify the simplest way on P2. So here you have some indeterminacy point. And I claim that this form is exactly algebraically stable for this compactification. And so you see that your map F, so it's a remark, side remark about that. F is algebraically stable with respect to the compactification. So C2 inside P2. If and only if something holds for the action on the tree, so you have F acting on the tree, it acts as a loxodromic element, so there is an axis in your tree where it acts as a translation. So we say that F is a loxodromic isometry, and it's going to be if and only if the axis of your isometry on the tree passes through the special vertex V2 the vertex of the identity. So here it's a remark after. So let me write it first. So it's if only if the axis of f acting on the tree contains the special vertex xy. So should take that as a hint that if you didn't know in advance what is a good representative to compute the dynamical degree, if you have an action on your simplex, maybe you have this kind of loxodromic action. So you have an axis. You try to put the axis in special position. So on your standard simplex, you have a good dynamical property. So we'll try to use that in dimensions 3 at all. Okay, 10 more minutes. Yeah. Okay. Yeah, so I should mention a third consequence. So these are kind of easy. The last one is not so easy. It was more or less the main result of my PhD a long time ago. That you have a Tits alternative for this group. So this group satisfies Tits alternative. Okay. So just okay, follows from yeah. So maybe it's a little optimistic, but at least this is one ingredient. So you understand the stabilizer of one vertex, the second vertex, the stabilizer of the edge, and to know that you want to understand the stabilizer of a path of length 2. So if you take a path of length 2 that is with center xy, so in fact, so this, I'm thinking of this path. So I go from V1 to V2 to V1 prime. So first, any path of length 2 with middle point of type 2, you can, under the action, you can bring it back to this one. So you have a transitivity property. But, there is only one kind of such path of length 2, center at the vertex of type 2. And I understand the stabilizer of such a path. It's a very simple group. So okay, follow is, but ingredient, the main ingredient is a follow. That the stabilizer of the path x, y, y is the following group. It's ax plus b, cy plus d. Just two copies of the affine one, and okay, that's a stabilizer pointwise. I don't want to switch this. So in particular, it's meta-abelian. So it's not abelian, but the first commutator group is abelian. The second commutator group is trivial. So it's solvable, and for the Tits alternative, you want to obtain either some solvable group or some free group. So the free group part is going to be some ping-pong argument when you have different axes. And the solvable part, you have to understand the stabilizer of some sequence of edges. And already for two edges, you have a solvable group. Okay. Yeah. No, I don't think so. I think here that's a nice thing about dimension 2, that any field is okay. Why are you worried? Yeah. GL2 FP bar is a linear group. It's covered by a Tits theorem.
And if you take two matrices in GL2 FP bar, there are in GL2 a finite extension of the
Yeah.
generated
Final group. Yeah.
but GL2 FP bar is not separable.
No, but for GL2 FP bar, the Tits alternative is for any finitely generated group. So, yeah, okay. So, yeah, okay. My statement was for the strong one, where you say for any group, and when you have characteristic P, for the reason you're saying, you have to state it for finitely generated one. And yeah, there is no escape to that. So, for finitely generated one, it's okay. Yeah, it's okay.
I have a question.
Yeah.
In your degree formula for F on the second one,
Yeah.
what's stopping you from composing a triangular map with its inverse and having it go back?
Yeah, because I don't want to do B1, B2 without A2 in the middle. And the A2 in the middle is not the identity. It's in A2, but not in B2. So it's an affine, which is not triangular, but in particular, it's not the identity.
Okay.
So in fact, I do something triangular, then I really do something linear that is not trivial, and another triangular in another direction, if you want. So because of this assumption, it's really not trivial. And in the graph point of view, it means that you do a path without going backwards. Okay, so if you remember my question, the next one was about normal subgroups in the groups. So I guess I will discuss that this afternoon. So this afternoon I will discuss a general theorem to produce normal subgroups when you have an action on a delta hyperbolic space. So here, for instance, the delta hyperbolic space will be the tree. The group acting will be Tame K2. And there is like a black box. So we'll describe a way called small cancellation theory. To produce many normal subgroups inside a group G acting on X, where X is a delta hyperbolic space. Okay, so the plan is to just describe the general statement, explain what we assume on G and on X, then observe that it holds for the action of odd K2 on the tree, and then try to replace odd K2 by Tame K3 and replace X, the tree, by the simplicial complex, or the triangular complex, and to try to make it work again. So that's the plan for this afternoon. Okay, thank you.